All right, although I was not invited to participate in the Mega Fave Numbers project, which is a project of mathematics YouTubers presenting a brief a description of their favorite number that is greater than 1 million. And I guess I haven't reached the level of mathematical YouTuberness to be invited or even acknowledged. And it's probably because my writing is very sloppy and I'm not particularly super hyper production professional. I've been doing this a long time, and my mathematics niche is actually a little bit more like physics, although I got to say I do a lot of just straight math. It is definitely geared toward physicists. Anyway, I don't feel too offended that I wasn't invited. I don't feel too left out. I don't feel too rejected. But regardless, I am going to jump in. They invite others to jump in, so I can do it. So I'm going to take a look at this, my mega fave number. I'm going to just put it down, write it down, and stick with me and see why I like it. All right? The number I'm going to pick for my mega fave number is 1,000,001. 1,000,001. Now, stay with me. I'm not being cheeky here. There's a point to this. I like 1,000,001 because it is the smallest number eligible for this project. Now, that to me makes it special, right? And the idea that I want to explore briefly is the idea of being special, a special number. And I'm no expert on special numbers. I'm not a number theorist. But this jumps out at me because when I was a kid, I was really attracted to fundamental proof about numbers being special that kind of got me interested in mathematics. And therefore, I want to share that feeling that I had when I was a boy and dealing with this question of special numbers. And the story goes back to this classic tale. Presumably it's true, but who knows? You know, these kinds of things can be apocryphal. But it has to do with this legendary mathematician named Srinivasa Ramanujan. I haven't met the man. He passed away. Boy, he passed away a long time ago. He passed away over 100 years ago. Look at that. But the story is that they were riding in a taxi. Wow, did they really even have taxis back then? Maybe this is apocryphal after all. But he was riding in a taxi with another mathematician, and that other mathematician noticed that the taxi's number was 1729, and that mathematician made the flippant comment, 1729, that's not a very interesting number. And Ramanujan, somehow, immediately, and that's supposed to be what makes him so interesting, is this did not take him long to figure out. And the question is wow, what kind of a man has a mind that can figure this out at the spur of the moment? But presumably, the story would go as he said, oh no, it is a very interesting number. It's actually the smallest number that can be expressed as the sum of two cubes in two different ways. So the fact that a number can be expressed as the sum of two cubes is interesting because any number can be expressed as the sum of cubes. That's kind of known. Obviously, because 1 cubed is 1, so you could just add up a bunch of ones if you had to, I suppose. But the idea that it can be done as the sum of 2 cubes is special. I mean, it's not 3 cubes, it's not 5 cubes, it's 2. And 2 is a small number. It's bigger than 1. It's not a perfect cube. That'd be cool. So, but if it was a perfect cube, apparently the first mathematician would have said, oh, we're in a cab, that's a perfect cube. So it wouldn't have been an interesting story at that point. But the fact that it can be done as the sum of 2 cubes in 2 different ways, that's cool. But the fact that it's the smallest number that can be done, that's what makes it special, right? It is special because it's the smallest number that is allowed in this analysis. So now the question then becomes, this story that I'm telling opens up the door to the question, is every number special in some way? Is every number special in some way? And that's a kind of a weird question because it all centers, of course, on what we mean by special. Can we quantify special in a way, or qualify it even in a way that's precise enough that we can say that every number is special? And when I was a boy, somebody showed me a proof, and the proof kind of went like this. All right, we begin by writing down all of the numbers, right? All of the natural numbers, starting 1, going up to infinity. And we write them all down, and then we postulate our conjecture. All numbers are interesting. That's our conjecture, right? And what we're going to do is we're going to begin by discovering a proof by contradiction, which is one of the fun parts about this. The proof by contradiction, and this is why, when I was first learned this, I was very excited by it because I didn't know about proof by contradiction, but when you see this exercise of proof by contradiction, you realize how powerful such a thing might be. But what we're going to do is we're going to assume that not all numbers are interesting. And obviously here I'm trying to say all natural numbers, right? Not all natural numbers are interesting. So what we're going to do is when we list all the numbers, what we'll do is we'll throw down a tag on the interesting ones. Well, 1 is certainly interesting. It's the smallest, and 2 is the only even prime. That's really interesting. 3 is smallest odd prime. 4 is a perfect square, blah, blah, blah. And we just keep going, and we throw on a tag on every interesting number. And then because of our statement, our assumption, right? This is assumed. We assume that this is true. We assume that not all natural numbers are interesting. Ergo, we are going to encounter some number, n, that is not interesting and does not deserve a little tag, right? Does not deserve a tag. And when we find n, then n will be the smallest uninteresting number. And you probably can see exactly where this is going, and therefore gets a tag as being interesting, because being the smallest uninteresting number makes it interesting. And in here lies the self-referential contradiction that makes this proof really more of a paradox, right? Paradox by contradiction, I guess is what we would call it. But this clearly is paradoxical, right? Meaning it's two things face to face that are contradictory, right? It is by definition the smallest uninteresting number, but it is also by definition interesting. This is a sort of a self-referential loop that breaks the logic here. So that's where this is not really a proof, right? Of course, when I first saw this, I didn't understand that at all, right? I was like, oh, okay, keep going, right? And eventually, well, not eventually, at this point, you realize, okay, this one's now interesting, so I go to some other number, m, that's uninteresting, and then, of course, this process repeats itself. That becomes the smallest uninteresting number, ergo, it becomes interesting, and now we see the contradiction. I assumed that not all numbers were interesting. I showed that if that was the case, then all numbers were interesting, ergo, this assumption had to be wrong, and my original hypothesis was true, and all numbers are interesting. And the reason that was so cool to me was because, well, crap, what if I picked, 17,242, right? Well, there's something interesting about that number. How do we figure it out? Well, what do I know how to do? I can factor the number. I can find its divisors. Remember, this is a high schooler or maybe even younger. I don't remember when this happened. Factor it. I can find the divisors. I can look at the digits. That's when I thought, well, let's see, digits. That's when I thought digits were interesting. I don't think about that anymore because I understand now about bases, right? What else could be interesting about a number, So anyway, this kind of got me the idea that everything, if you look at it deep enough, at some level, there's something interesting there. And it could be so hard to find that it actually exposes the break between where mathematics is just deeper than humans can think. And if you don't find something interesting about a number, it's your fault, pal, right? It's not the number's fault. There's something there. And how do I know? Because of this proof, right? Now, I want to emphasize that I don't think this proof can be taken seriously because, as I say, as soon as you define anything to be interesting, as soon as you take the word interesting and you give it any kind of definition, the whole thing falls apart, right? So, for example, if my definition of interesting is that it's got to be a perfect square, it means the number to be interesting must be represented as n squared, then the number 1 is interesting and the number 4 is interesting, and then 2 becomes the smallest uninteresting number. But the property of being the smallest uninteresting number, when interesting is defined like this, no longer makes it interesting. That is insufficient to make it interesting. So the slightest pressure on the word interesting destroys this proof and breaks the self-referentiality that causes the fundamental problem. Okay, so in some sense, the idea of a number being favored or interesting is absolutely 100% arbitrary, and therefore I have every right to choose this number to be interesting because it is the smallest number, which makes it unique. It's definitely unique, right? Special might be unique, right? It is definitely the first unique number that is the smallest unique number, the first unique number that is eligible for this project. Now, okay, so to be fair to the spirit of the Mega Fave Numbers project, and to also be fair to the spirit of the paradoxical proof, now we're staring at a number and there's something special about it. Let's presume that the conjecture is actually true, despite the fact that our proof of it is pretty sketchy. What can we find that is special about 1001? Now, I am no super mathematician from 1920. We're really lucky we had those guys back then before computers where they really had to think about these things. I've been studying a lot about special functions and differential equations, and all of that stuff was invented somewhere between like 1880 and 1930. And we probably don't spend enough time reconstructing all of that just from foundational principles. But, I don't have the kind of brain that can just dig into this. So I did look at different kinds of properties of this number that are cataloged, and I found a few. The problem is a lot of the properties about this number are based on the idea of being a palindrome. First of all, it is a palindrome, but it's not the smallest palindrome. It's also based on the idea that if you square it, you get a palindrome. So you got a palindrome squared, that's a palindrome. If you cube it, it's a palindrome. If you raise it to the 4th power, it's a palindrome. So there's all these things about being a palindrome. I think it's also got this interesting property that if you take its divisors, you take all of its divisors, 1 times, and multiply all of its divisors together, you get a palindrome. That is an interesting idea, I guess, right? I mean, it is semi-prime, right? So this number is semi-prime. So it's the product of 2 primes. Those are the 2 primes. Obviously, if you multiply these numbers together, you'll get this number, and that number is a palindrome. So if you take its divisors that are less than it and multiply them together, you get a palindrome. And the fact that this number squared is a palindrome means that this product times that number, well, that's equal to the square of this number, and that's a palindrome. That's this palindrome. So, okay. So you got all these palindrome rules. The problem is palindromes are heavily dependent on what base you're in, right? So, for example, this super duper cool palindrome is all of a sudden this thing in hexadecimal. So clearly palindromes, are they really interesting? I mean, it's attached to the arbitrary human convention of what base you're in. So, meh. So anything that's related to being a palindrome, I gotta say, I don't think it's interesting at all. So all the palindromic ideas are out. So what else have we got? Well, how about this? This is a true mathematical statement which asserts essentially that 1,000,001 is part of a Pythagorean triple, right? That's fun. And if you're still into palindromes, you could say, oh, it's a Pythagorean triple where 2 of the members of the triple are palindromes, right? So all of a sudden it's kind of weird. And I guess the number itself, not only is the triple got this as a palindrome, but the actual square, because we already know 1,000,001 squared is a palindrome, that's a palindrome. Palindromes are out. We got to get rid of palindromes. But the fact that it's a Pythagorean triple is okay. It's not the smallest Pythagorean triple. It is primitive, though. This is a primitive Pythagorean triple, so that's good. So it's not just some arbitrary Pythagorean triple. It's primitive, but it's not the smallest one. So I don't know how far you can get with that. It also solves something called a certain version of what's called the Pell Equation, which I'm not going to get into. But the Pell Equation is, well, specifically it solves this version of something called the Pell Equation. There's a lot of different Pell equations depending on how you select this number. Actually, depending on how you select that sign, too. Apparently, they come in the plus and minus form. I'm certainly no expert on the Pell Equation. I only learned about it while trolling for facts about 1001. And in fact, the more I troll, I realized this is 1001, 1,000,001. 1,000,001 is not even a solution to this thing. If you look carefully at the dictionary of integer sequences where I was doing all my trolling, y is actually 53 times 1,000,001, and x has to be 500 times some other number, which is actually oddly close to 1,000,001. It's 1,000,003. If you take those two products, evidently that solves this Pell equation. The Pell equation is pretty cool. It's actually like, it's a lot like Pythagorean triples as far as I can tell, right? It's a relationship between the squares of things where you throw in some arbitrary integer and then you add or subtract one. I don't know. Anyway, there's no way I'm going to call that interesting. You'd have to show me why the Pell equation was super interesting and why this connection between the solutions is interesting and why the y solution is interesting and then why it being split into two numbers is interesting, etc., etc. This isn't even a prime number, right? So it's not even the prime factor of a solution or something. Anyway, the point is I got to say, I think 1,000,001 is actually, it might actually be uninteresting, which is, hey, no surprise, because we have shown that the proof that all numbers are interesting is very questionable. You know, the irony here is it may in fact be that all numbers are interesting, right? And I think if we said something like, if a number is the smallest number with a certain identifiable property, it is interesting, right? The problem is even if you said that, a number being the smallest number than an identifiable, that doesn't solve this problem, right? Because, you know, if all I knew about was primes and squares, I might say, oh, 5 is, it's not a square. Oh, it's prime, but it's not the smallest prime, right? So 5 is uninteresting. But it has the property of being the smallest number with a certain property, the property of being uninteresting. So I haven't even saved it by demanding the smallest number, as far as I can tell. So anyway, it's ironically may be that 1,000,001 is in fact uninteresting. Okay, so that's my entry, 1,000,001. The reason I chose it is the smallest number with a certain property, and I'm emphasizing the arbitrary nature of that by choosing that certain property to be the lower boundary of the megaphase number project. And then, ironically, we explored a little bit about the properties of 1,000,001, and I sort of struggled to find any of those properties as being interesting. And in fact, I wonder if this basically means that there is no such thing as interesting, right? Interesting is completely a human construction. It's something that's going on in our heads that has no relevance to nature whatsoever. Something can only be interesting in the context of some kind of theoretical foundation that might exist out there. That's sort of an idea that I think is worth exploring. I mean, we humans see patterns. We like to think of things in terms of squares and cubes, and why not exponents that are 7? And well, we like squares and cubes because they're kind of small. You know, this is all sounding very brain limited, right? And evolution arbitrary to me. So I'm not quite sure what's up. On the other hand, if you chose numbers that had physical relevance, right, like say h bar or the speed of light, Now I think we're in the realm of something interesting because we have sort of experiments to go on that we can lean on those experiments to say that, you know what, beyond being human, if humans weren't here or if humans were something else, if we were very advanced sea otters, for example, we might still come up with these numbers. But, we may not be as interested in little numbers like 2 or 3. I don't know. So there's my entry. If you can find something really, really interesting about this that might move my needle, I'd be really appreciated if you mentioned so in the comments. And that is my entry for the Mega Fave Number Project.